Go. Good afternoon, everybody. Welcome to another exciting afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. And I hope you're all ready for an exciting afternoon. Can you imagine we've already been together 2 weeks? Boy, time flies when you're having fun with organic chemistry. Now, a couple important announcements. One, don't forget, a week from today, I will be giving test number one. I've already posted an announcement that test number one will cover the hydrocarbons, alkanes, cycloalkanes. It will also cover alkenes, double bonds, alkynes, triple bonds, and aromatic compounds, otherwise known as benzene rings, or at least include benzene rings. And that will be all that will be on test number one. Next Tuesday, this coming Tuesday, I will give my world famous review for the next test. In this case, it's test number one. Students have told me it helps them. So guess what? I do that. And don't forget, the laboratory on alkenes was due yesterday. If you haven't gotten it in, uploaded it, make sure you upload it. And the lab we did yesterday, electrophilic aromatic substitution, is due next Monday. Now, one of the things I was thinking about this morning, I said, oh no, I forgot to teach you something important. And that is when we talk about alcohols, there's a certain alcohol, actually a diol, di meaning 2-OL alcohol, that I should talk about. And that's bisphenol A, also known as BPA. Oop, wrong thing. Does everybody see bisphenol A on your screen now? Thank you. All right. Now, bisphenol A has this structure. Let me move me and everybody else out of the way. And it's two benzene rings. Here's a carbon, there are methyls here, and it's an alcohol, diol, because you have a hydroxy group on a benzene ring, two of them. And this is BPA, bisphenol A. Now, bisphenol A is used for a number of things in our daily life. Unfortunately, a number of years ago, they found out that bisphenol A, your body thinks of it as estrogen, a hormone. And if you're pregnant or if you're young, that could cause some serious damage to your body. Not good. Now, where can you get bisphenol A? Well, bisphenol A is used to react to make a coating for metal cans, like soup cans. Now, most of the time, you don't have to worry about unreacted BPA getting into your body. By the way, BPA is not something Mother Nature ever made. And a number of years ago, they did a study and they figured out 90% of Americans, like you and me, have bisphenol A in our body and in our blood. It gets in there. Now, if you know anybody who's pregnant or has little children, there's certain ways you can get BPA from metal cans, anything that's acidic. Example, if you get tomato products in metal cans, be careful. Now, the other way, the most easiest way to get BPA into your system, bisphenol A, is the receipts you get from a supermarket or a gas pump, the thermal printed receipts you get when you buy gas, go to the supermarket, they have a coating on there made from BPA. And that coating, when you touch the receipt with your bare hand, you can get it into your body. It absorbs through your skin. So if you know anybody who's pregnant or young kids, don't let them touch those receipts or put on rubber gloves. And that's my public service announcement for today. Oh, one other thing I forgot to mention, but I'll mention again on Tuesday, but I should do now, and that is for test number 1, 2, 3, 4 in the final, your friends are the following that you should remember. 1, how many bonds to carbon are there? Oops, let me fix that finger. 4. Remember, 4 bonds to carbon. Next, do you break carbon-carbon single bonds except for combustion when you burn it? No, that should also be your friend. And the last one, when you look at an organic molecule, look for what's different. Look for what's not a carbon-carbon single bond or carbon or hydrogen, because that's where the fun is going to happen. And that will help you, A, name it, nomenclature, and B, how it reacts. So those 3 things you should remember. How many bonds to carbon? 4. Do you break carbon-carbon single bonds? No. And when you look at a molecule, look for what's different. What's not a carbon-carbon single bond or what's not carbon or hydrogen atoms should get your attention like that. Hopefully that got your attention. All right, now let's get back to alcohols. Remember, alcohols will not be on test number 1, but it will be on test number 2, which is coming up sometime in the next couple of weeks. I don't remember when, but I'll get an announcement when that is in time, and it's in the syllabus. All right, we talked about how do you make alcohols. One way is this way, double bond plus acid and water. And let me just do a quick thumbs up, people. Do you see synthesis of the, thank you. All right, now let's talk about reactions of alcohols. But before we do, I want everybody take a deep breath, let it out, take a deep breath, let it out. Are you nice and relaxed? Stay that way. This coming general reaction, the one I'm going to talk about now, is one of the more challenging. Relax for students to master it first. Once they practice, they get it. But at first glance, it's challenging. I'll be honest, it was for me too. But students have mastered it. Now, if you take an alcohol and react it with acid, sulfuric acid, H2SO4, the little triangle means heat. And sometimes, not always, I'll put down a number saying it's pretty high heat. You lose water from here. Hydroxyl group and an adjacent hydrogen and a carbon bonded to the hydroxyl group, you lose water, and between those 2 carbons, you form a double bond. This is called dehydration of alcohols. And why? Because you're losing water. Dehydration is loss of water. Now, there's possibilities of where this double bond could be if you also had a carbon on the other side with a hydrogen. And it turns out another great Russian organic chemist figured out how to know where things go if you have a choice. And this is called Zayces Rule. And Zayces Rule is the major product in the intramolecular alcohol dehydration reaction is the alkene that has the greater number of alkyl groups attached to the carbon atoms of the double bond. And you look at that and go, what? What? Well, let me explain it Dr. White's way so you won't have to go, what? Hopefully you'll never have to do that in my class. Oops, got to turn this on. All right, let's get working. All right, let me just check because I've been lazy. Everybody see the reaction on the whiteboard? Now you should see it. All right, I assume everybody can see it. And let's do it. Now, what are we reacting? This molecule with sulfuric acid and heat, high heat. And a lot of times in the test, I'll just put the triangle, not a temperature too, like 180 degrees C. And what is the general reaction? And that's dehydration of an alcohol. And you lose water, and it follows Zayces Rule. Now, if we look at this molecule, and first of all, I'm missing a hydrogen. No, I'm not. Here's our carbon with the hydroxyl group, this carbon. And where's this carbon? Well, we've got two choices, here or here. Both have a hydrogen that can be lost. Now, if I lose this hydrogen between this carbon and the hydroxyl group carbon, I'll form a double bond. And let me change something, I apologize. Oh, that's not what I wanted to do. If I lose the hydrogen here and the hydroxyl group, I'll form this alkene. I've formed a double bond. Now, if I lose the hydrogen from B, carbon B, and the hydroxyl group, I'll form this molecule. Now, how do we do Zayces Rule? Zayces Rule, the easier way to remember is you count, and listen carefully, you count the carbon atoms directly bonded to the carbons of the double bond. You count the carbon atoms directly bonded to the carbons of the double bond. In A, it's this one, and this one. So that's 3. In B, there's only this one. You don't count this or this, only the carbon, and listen carefully, atom directly bonded to the carbons of the double bond. Therefore, this one has only 1. And Zayces Rule is the one that has the most carbons is the major product. Now, to make your life easier, I'm going to modify it slightly and say the one with the more carbon atoms is what you get. That's the only answer. Therefore, this is not what you get, and this is the product you get. And that's how you use Zayces Rule. Let's go through it again. If we look at this molecule, we'll look at it and say, what are we going to have happen? Oh, I've got a hydroxyl group. I'm reacting with acid and heat, sulfuric acid. You get dehydration. We've lost water. I don't put it down here, but you also make water. And you form a double bond. And you form a double bond between the carbon with the hydroxyl group and an adjacent carbon with a hydrogen. Now, in this molecule, we have 2 adjacent carbons with hydrogens, A and B. If we lose the hydrogen from A in the hydroxyl group, we get compound A. If we lose the hydrogen, the hydroxyl group from B, we get compound B. To do Zayces Rule, the way I teach it, and it works quite well, always the same as the way it was officially in the page I showed you on the slide, the molecule you get is the one with the most carbon atoms directly bonded to the carbons of the double bond. And therefore, in A, the carbon atoms directly bonded to the carbons of the double bond are the 3 green circles. In B, the carbon atom is only that one circle. And which is greater, 3 or 1? And we all picked 3. And therefore, that's why A is the product you get per Zayces Rule. And that's how you do it. Now, this is pretty complex. I'm not lying to you. Well, I'd never lie to you, but now you know. And let me have you try one. And why don't you try this one? What would be the product or products hint? You only get one per the way I teach it for this reaction. Your turn. Oops. All right. Anybody need more time? And I think everybody's done. So let's do this. All right. What do we have that's different? Ooh, hydroxyl group. And I'm reacting it with acid and heat. And I know this is a dehydration. So I have adjacent carbon with a hydrogen. You lose that water. And you don't have to put the water down, but I will today because I just asked for the organic product or products, and it follows Zayces Rule. When I first started teaching, I used to write it out, which I would invariably make a spelling error. I don't know if I told you I was first one down always in the spelling bee, but now you know. And I just, like Markov, put the first letter, but I do say his name to honor him. So here's our hydroxyl group. Where's an adjacent carbon? There's one here, then there's one there. If I lose this hydrogen and this hydroxyl group, what product will I get? Well, do you break carbon-carbon single bonds? No. So I have 2, 4, 5 across. I have a methyl group here, and these 2 carbons, between them, I'll form a double bond. And next, if I lose the hydrogen from B in the hydroxyl group, I'll still have 5 carbons, methyl group there. But now between this carbon and this one, I'll form a double bond. And the question is, which one do you get? And now we'll use Zayces Rule. And Zayces Rule is you count the carbon atoms directly bonded to the carbons of the double bond. So in this one is that carbon. You don't count that. This is the one I'm circling. This one and this one. And this is 3. Now, common mistake down here, student will say, oh, 1, 2, 3, 4. No, it's a carbon atom directly. And that's that. So that'd be 1. And Zayces Rule is the one that has the higher number you get. So the answer is A. That's what you get. And that's how you do Zayces Rule. Now, what I like to do when I'm teaching this is let you try one, I've done one. In the problem set for alcohols, which you'll do after test number 1, you'll have more practice and we'll go through it again. And now I'd like to move forward. Now, next couple reactions are pretty easy and fun. If you take an alcohol and react it with an acid, HX, where X here can be chlorine, bromine, or iodine, you replace the hydroxyl group with the halogen on the carbon that the hydroxyl group was on. And you also get water. I put this down here. I don't know if I told you the story. A couple of years ago, I was teaching the same course at College of DuPage, COD, and I had 2 sisters. Actually, they were twins, identical twins, who were taking the course. And they both got upset. I mean, really upset when I didn't put in all the chemicals. So a lot of my slides, I now put that in there, but on a test, you don't ever have to put down water. But oh, they get upset. The only way I could tell them, one had a blonde streak that she had in her hair and the other didn't. Other than that, they were identical. Personalities were pretty close too, which is unusual for twins. But anyways, let's look at this reaction. And remember, if I'm reacting something, I can do plus or put it above the arrow. For this one, I like to do this. And the question is, what's happening? Well, you look for what's different. What's not carbon, what's not hydrogen? Oh, an alcohol. We're reacting with HX, where X can be chlorine, bromine, or iodine. In this case, it's chlorine. And you replace the hydroxyl group, whoops, with the halogen. Now, in this case, what's R? Remember, R is like X and Y in math, but in organic chemistry, something with carbon and hydrogens is that. Remember, the halogen goes on the carbon where the hydroxyl group was. And that's this one right here. And that's chlorine. And that's 1 bond to carbon. I know there are 4 bonds to carbon. And that's the molecule I have. Let me remind you, by doing these reactions, I can make new molecules that I use to do many things, make other new molecules, or they're used in many things in our daily life. And just like how a carpenter knows how to use 2x4s, 4x8 panels, and all the things, screws, etc., to build things, organic uses these general reactions to build things. And here's one for you to try. Give the organic product or products for the following reaction. 3 points each. And when you're done, don't forget to give me a thumbs up. I see one person done. I see two. I think everybody's done. I better get to work. If we look at this molecule, what's different? Ooh, look for what's not. Carbon, carbon, single bond, carbon, hydrogen, oxygen with a H on it, hydrogen, bond to carbon, alcohol. Reacting with HX. And remember, X can be chlorine, bromine, or iodine. And I replaced the hydroxyl group on that carbon with the hydroxyl group with the halogen. What's my R group? This. And do you break carbon-carbon single bonds? No, so I have 4 across. I have my methyl group here. And on this carbon, where the hydroxyl group will be this carbon with the halogen. In this case, it's iodine. If you have it coming down, that's fine too. And I know there are 4 bonds to carbon, so I can put in the hydrogens. And I'm done. And that's how you do it. Oh, this is fun. We got to do another one. And have some fun. Give the organic product or products to the following. Remember, keep your eyes on your own paper. No, I'm just kidding. I see one person done. If you're not, take your time. I leave everybody time to finish. I think everybody's done. So let's do it. What's different in this molecule? What's not carbon, hydrogen, or carbon-carbon single bond? Oxygen and a hydrogen and a carbon, that's an alcohol. And we're reacting with HX. In his case, X can be chlorine. In our case, it is bromine, or it could be iodine. And it replaces on the carbon with the hydroxyl group, you get the halogen. Do you break carbon-carbon single bonds? No. Here's our R group. Therefore, I'm going to have my ring. On this carbon, there's 2 methyl groups. And the carbon with the hydroxyl group will now have the halogen, and that's bromine. And I'm done. On test 2, unlike test 1, I will have up to 3 synthesis problems. So let's practice one. Well, it's a pretty molecule. Now you know he's an organic chemist. What would be the starting material, the reactant that you react with HI to make that molecule? Your turn. And when you're done, don't forget, thumbs up. I never ask. Make sure your thumbs are clean when you do that. No, I'm just kidding. If you want to use a thumb puppet, you can do that too. I've never said that, and I better never say it again. All right, let's do it. Everybody's done. How do we do it? When you're doing synthesis, you look at what are you trying to make and what's different. In this case, halogen on a carbon. And what's my R group? This. And what would we start with? Notice we're not adding carbons. So whatever we end up with, we better have started with the same number of carbons. Let me make some room here. Notice we have 1, 2, 3, 4 across. And on this carbon, I have 2 methyls. This is a carbon with the halogen. How do we do that? Take an alcohol, react it with HX, because that's what this is. And X can be chlorine, bromine, or in our case today, now, iodine. And you replace the hydroxyl group with a halogen. So whatever carbon had the halogen will be the carbon with an alcohol. And I know there are 4 bonds to carbon. So there's my product. And that's how you do it. Now, one of the things we really won't get into too much in this class is what happens if you have more than one functional group in a molecule. Well, it turns out I'm going to show you something why sometimes this reaction can be a problem. And then I'll show you how organic chemists got around the problem. All right, what I'm going to write on the whiteboard, notice how I named it after me. Don't copy this down, but it's to illustrate a point. What happens if you have this molecule and you need to replace this hydroxyl group with a chlorine, but you still need to keep the double bond? So you say, oh, I know, I'll do HCl because alcohol plus HX, where X can be chlorine, bromine, or iodine. You replace, oops, let me do it right. You replace the hydroxyl group with X. So you say, oh, I'll do that. But we have another functional group. That's the double bond. And you learned this. And hopefully you've learned it, you'll learn it for test 1. You have a double bond reacted with HX. You break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule. So if I react this, some of this might react, some of this might react, and both might react to give you something like this. Again, you don't have to write this down. And you'll get this. In reality, you could get plus 2 other products where the alcohol only reacts at a double bond. In other words, you get a mess, not what you want, which would be where you kept the double bond and only the hydroxyl group was replaced by chlorine. So what do? Well, you learn and use the next reaction. And this was a dilemma, and I don't know who came up with this. That's the reaction of alcohols with thionyl chloride. SOCl2 is thionyl chloride. Now, I have all the products because of the twins got mad, and I don't want them mad at me. But anyways, You take an alcohol, react with thionyl chloride, only with hydroxyl groups. This will not react with double bonds or triple bonds. You replace the hydroxyl group with a chlorine. So this is the way to get around it. And around it meaning the problem I just showed you. And what's the product of the following reaction? What's different? I'll do this one. An alcohol. What are we reacting with? Thionyl chloride, SOCl2. What does it do? It replaces the hydroxyl group with a chlorine. This will not react with double bonds or triple bonds, but I won't do that on my test ever, because this class I keep the one functional group. What's my R group? This. Therefore, do you break carbon-carbon single bonds? No. 1, 2, 3, 4. The carbon with the hydroxyl group will now have a chlorine, and I know there are 4 bonds to carbon, so I can put in my hydrogens. And that's how you do it. And it's your turn. What would be the product or products for the following reaction? 3 points each. And it's starting to get cloudy out there. I sure hope we get the rain they're promising tonight. My lawn and bushes can use it, my trees too. All right, everybody done? Let's do it. What's different in this molecule? That carbon or hydrogen? Oxygen with a hydrogen. This is an alcohol. What are we reacting with? Thionyl chloride. What do you get? You replace the hydroxyl group with a chlorine on the carbon with the hydroxyl group. What's R? That. Do you break carbon-carbon single bonds? No. This is this carbon, which is this carbon. I'll replace the hydroxyl group with a chlorine, and lo and behold, that's what you get. Oh, let's have some more fun. And there you go. Some more fun for you. What are the organic product or products for following reaction? By the way, I'm secretly training your brain how to look at molecules. It can't be secret now. I just gave it away. Shucks. Well, my webcam people are done. How about the rest of you who have to use the emoji? I think everybody's just about done. So I better get to work. What's different in this molecule? What's not carbon or hydrogen? Oxygen and a hydrogen? Alcohol. Reacting with thionyl chloride. And you replace the hydroxyl group with a chlorine. What's my R group? This. Do you break carbon-carbon single bonds? No. So it all comes along for the ride. and the carbon with the hydroxyl group gets the chlorine. And I see I have a question, so I better check. Ah, an answer. All right, let's do a synthesis because that's the fun part. And there's some fun for you. What would you react with thionyl chloride? What would be the starting material to make that molecule? Now, at my level, you're not told you react with thionyl chloride. You say, I need to make that compound. How do I do it? And that's where you use these general reactions. Well, I see two people are done, but take your time. All right, looks like everybody's done. I better get to work. What's different? What's not carbon? What's not hydrogen in this product? A halogen. And I can just say the rest is carbon hydrogen. So I can say it's an alkyl halide, where this is my R group. Or actually, for this reaction, it's a chlorine. How do I know that? Because I looked over here and realized, oh, I better use that chlorine. What do you react with thionyl chloride to make that compound? An alcohol. The R group is this. Am I adding carbons? No. So that means I will start with the same number of carbons that I end up with. And the carbon with the halogen in the R group will be the carbon with the hydroxyl group in my starting material. And now, time to put in hydrogens, because I know there's 4 bonds to carbon. And that's how you do it. All right. Now, normally I would go a little longer and we'd take a break, but this would be a good time to take a break. Come back in 5 minutes. I can go stretch, and I'll see you in 5 minutes at 1:50. That's when your digital watch says 1:50. See what a nice guy I am? See you in 5. time to start again. All right, everybody back? All right. Now, one of the questions you should be asking me or yourself more and more as we're getting into organic chemistry this semester is, why am I learning this stuff? And the obvious answer is someone told you have to take organic chemistry to get into a program or to get into school, like nursing school or whatever program you're trying to get into, like physician's assistant. So that's why you're taking it. But why learn organic chemistry? Well, let's find out. Now, how many of you are familiar with artificial sweeteners? And one of the more widely sold or popular artificial sweeteners is Splenda. And if we look here, Splenda, that's an artificial sweetener. And the market worldwide is, I don't know how many billion, and it's quite large in the United States. And Splenda is probably one of the top, if not the top ones. Now, what's in Splenda that makes your tongue tell your brain, ooh, this is sweet? And the molecule is called sucralose. Now, here's the structure of sucralose. And wow, that sounds familiar. Let's look at another molecule. Can everybody see this here? This checkered thing with the little checkers, I don't know. Anyways, that's sucrose. Sucrose is also known as table sugar. I'll teach you more about it. Notice it has all these hydroxy groups on carbon. Each bend in a line is a carbon. The darker shows what's called stereochemistry. If we look at the difference between sucrose and sucralose, what they've done is replace a couple of the hydroxyl groups in sucrose with chlorine. How would you do that? Well, if I were doing it, I'd either use the reaction of sucrose with HX or sucrose with thionyl chloride. So why are you learning that? Because those reactions help make products that are sold in our everyday life, like this one, sucralose to make Splenda. Now, personal thing I should talk to you about. Now, don't write the structure down. I just wanted to show you why are you learning this stuff? Because it helps make molecules that are used in our everyday life. Now, a number of years ago, I don't know, 4 or 5 now, two things. One, I saw, and I think it was in the New York Times, there was an amazing article from these two medical doctors. What's the term for those who specialize in stomach area? Gastroenterologists or something, I don't know. Medical doctors who specialize, and both of them were overweight. Tell me about it. But anyways, and they had been taking artificial sweeteners. They were wondering, how does that affect my system? And they were able to look at the microbes in your stomach, the flora, otherwise known as the probiotics, I think. And I'm a chemical doctor, not a medical doctor. So, but anyways, I remember this because I was drinking a lot of pop at that time, and it was all artificial. I'm a Dr. Pepper and a Verner's person. If you haven't tried Verner's, you're missing some of the greatest pop ever. By the way, I've lived most of my life, except for 5 years in the Chicagoland area. Those 5 years I was in East Lansing, Michigan, getting my PhD. And the stuff we have in a can or a bottle, plastic or glass that's carbonated, non-alcoholic. I call pop, not soda, because I'm from the Chicago area. But anyways, in that article, they did some measurements and found out if you consume something with artificial sweetener in it, it killed all the probiotics in your stomach, or a good part of it. And I'm not going to go into the messy way they found that out. Never mind. But anyways, I'll let you imagine what they measured that comes out of your pot. But anyways, and within about 24, 36 hours, that would come back, most of it. Well, what they figured out is when that happened, it made you more hungry, which is taking something that's trying to help you lose weight makes you hungry. And also it has other detrimental aspects. Now, around that same time, I had made something and it was sitting around too long. I didn't realize it. That went bad in my refrigerator, and I gave myself food poisoning. Not fun. Not fun. Well, anyways, I went to my doctor and I was getting better. And I just read that article and I asked him about it. And he said, yeah, I have problems with artificial sweeteners because of my stomach. He's thin, it wasn't his weight. And so I don't touch them. That's probably true. Well, anyways, up to then, I had used no sugar. I stopped using artificial sweeteners. I went back to using sugar, like in my tea. I don't drink as much pop, but I went to normal pop with fructose and sucrose, sugars. And lo and behold, I started losing weight. So that's my own personal experience, but I thought I'd let you know. And always ask, why am I learning this stuff, organic chemistry? And you'll find out. And I'll tell you if you're not sure. All right, before I do the next reaction, I have to teach you something that I'll do on my whiteboard. When we talk about alcohols, turns out there are three types of alcohols. This will never be on a test, but I'll use the terminology, so that's why I'm talking about it. Now, the first alcohol has a carbon with a hydrox group with only one R group on it. And this is called a primary alcohol. And like I said, I'll never put this on a test, but I will use this terminology in class. And primary alcohols, if I haven't told you already, organic chemists are lazy, are abbreviated like this. One with a degree sign means primary, ROH, alcohol. Now, if you notice here, this is the alcohol, and this carbon has not one, but two R groups. And since they can be the same or different, I use R and R prime, just like in math, use X and Y. And this is called the secondary, 2-second, like in second base in baseball. This is secondary alcohol, and it's abbreviated 2 degree sign, ROH. And the last one, notice the carbon with the hydroxyl group has not one, not two, but three R groups. Notice I have R, R prime, and R double prime. That means they can be the same or different. The R is something with carbon and hydrogens, and this is called a tertiary alcohol. And again, I'll never ask what's a primary, secondary, tertiary alcohol on a test or the final, but I'll use the terminology in class. You should know what I'm talking about. And this is abbreviated with a 3 degree sign, ROH. So you have primary alcohol, one R group on there, secondary, 2 tertiary 3. Now, for many of the reactions, the ones I've already shown you, they react the same way. There's some reactions where there's differences between primary, secondary, and tertiary alcohols. And now that you know about it, I can talk about one of those reactions which has a difference. All right, everybody have this copy down who wanted to copy it? If not, you can always go back and look at the video. Remember, thank you for making Dr. White a YouTube star. Not really, but it feels good to say it. Now, the reaction I'm going to talk about is oxidation of alcohols. Now, in chemistry, we have oxidation reduction reactions. I'm not going to go into what oxidation is, but originally oxidation got its name from oxygen reacting with things. Now, if you notice here, we have a primary alcohol. And I'm reacting it with what? What's that O in a bracket? This is shorthand for oxidizing reagent. Now, if you were chem majors, I'd make you learn examples would be such as potassium permanganate or sodium dichromate. And there are other oxidizing agents. For this class, I'm going to use what organic chemists use as a shorthand, a bracket. If I can make another, let's make a nicer bracket for you people. Oxygen, O, close bracket. And that means any of these oxidation reagents or otherwise. And what happens is when you oxidize an alcohol primary, you lose this hydrogen and this hydrogen, and between the carbon and the oxygen, you form a double bond, which I have written this way, and I really should have done that. I could have also done this. And you form, and this you're going to learn in 2-3 chapters, is called an aldehyde. And I should tell you, Dr. White loves aldehydes. They've been good to me. I've been good to them. I really do. So this is oxidation of a primary alcohol. So let's practice it. And let me do this one. And the question would be, what's the organic product or products are the following? And by the way, for my PhD thesis, I made a lot of aldehydes and ketones, or I'll get to the ketones, aldehydes, using this type of a reaction. Not this reagent, but other ones. And what do we have here? Now, as soon as you see oxidizing reagent, O in a bracket, you know you have to consider primary, secondary, and tertiary alcohol. And this is a primary alcohol. It oxidizes. You lose a hydrogen here and hydrogen there, and you form a carbon oxygen double bond. By the way, you can write it this way, and you can also write it this way. I think this way looks cooler, so that's the way I'm going to do it. You can do it either way on my test. Well, what's my R group? This. The carbon with the hydroxyl group will be the carbon double bond to oxygen. Do you break carbon-carbon single bonds? No. So I have 3 across. The carbon with the hydroxyl group will have a hydrogen, and it'll be double bonded to oxygen. And that's how it works. And it's your turn. What would be the product or products for the following reaction? Well, it looks like everybody's just about done, so I better get back to work. What do we have that's different? Hydroxy group on a carbon. We're oxidizing it. What kind of alcohol is this? It's a primary alcohol. And when we oxidize it, we lose the hydrogen there and form a carbon oxygen double bond. And I'll teach you more about that. My knowledge of aldehydes helped my last and first patents come to fruition. In other words, I figured out using aldehyzing. Anyways, what's my R group? What's ever attached to the carbon with the hydroxyl group? Do you break carbon-carbon single bonds? No. This carbon is this carbon, which is this carbon, which is this carbon, which will be double bond. The oxygen have a hydrogen. Remember, there are 4 bonds to carbon. This carbon has 2 from here, hydrogen and a single bond, 4. And I'll put in the rest of the hydrogens. And I'm done. Oh, we got to do another one of these. Have fun. Give the organic product or product for the following. I think I mentioned it. I learned when you draw structures with alcohols and other molecules, put the functional group on the right, and that's a habit I'm not going to break in heaven. I'll check the non-webcam people. Are you guys done, non-webcam people? Yes, you are. All right, let's do it. What's different? Ooh, I forgot to put the other brackets, sorry. But anyways, what's different in this molecule? Hydroxyl group on carbon, alcohol. I'm oxidizing it. That's a primary alcohol. What are you oxidizing? That alcohol, and what do you get? An aldehyde. And I'll teach you in a couple of chapters what are aldehydes. And what's my R group? This ring with the 2 methyls. It's attached to this carbon, which is this carbon, which becomes this carbon. Do you break carbon-carbon single bonds? No. And this carbon, which is this carbon, is double bond to oxygen and has a hydrogen on it. Ooh, we're getting into some good molecules now. Why don't you try this one? What would be the starting material to oxidize to make this molecule? I see 2 people I think are already done. Only 2 people with their webcams on. 3. I think everybody's done. So I better get to work. Thank you. I give myself some space here. And what's different here? Ooh, oxygen, double bond to carbon. And what's attached to that carbon with the oxygen, I'll call R. And here, what do we react oxidize to make an aldehyde, a primary alcohol. And therefore, what's my R group? Methyl. The carbon with the double bond to oxygen will be this carbon with the hydroxyl group. And that's how you do it. So this is oxidation of a primary alcohol to an aldehyde. Now let's move on. A similar thing happens with a secondary alcohol. This is a secondary alcohol. If you oxidize it, you lose this hydrogen and this hydrogen, just like you had before, and we call the product you make a ketone. And Dr. White loves ketones too. Good part of my PhD thesis dealt with my special knowledge when I was investigating special things with ketones. And therefore, that's what happens when you oxidize. Remember, O in a bracket, close bracket, is oxidized a secondary alcohol. You lose this hydrogen, this one, and you form a carbon-oxygen double bond, which we call a ketone. And if I look at this molecule, and if I react it with oxidizing agent, O in a bracket, what are the product or products, or what is the product or products? And what do we have here that's different? Oxygen on a carbon, but now look at this alcohol. It's a secondary alcohol. And when we oxidize it, it's a secondary alcohol. Remember the shorthand for primary, secondary, tertiary. You lose this hydrogen, this one, and form just like a primary alcohol, but now you have two R groups on that carbon, and you get this, a ketone. So what's my R group? Doesn't matter what you call R and R prime. Here's the carbon with the hydroxyl group, this carbon. Do you break carbon-carbon single bonds? No. 1, 2, 3, 4. That will be double bond to oxygen. Now you could have the oxygen on top. I just happened to write it down. Another way of drawing this molecule, which I will in the future do, because I'm sort of showing bond angles of the double bond, would be this. And they're both the same molecule. And that's how you do oxidation of a secondary alcohol. Your turn. Give the organic product or products to the following reaction. I think everybody's done, so let's do it. All right, if we look at this molecule, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? A hydroxyl group on a carbon. But we're oxidizing it. O in a bracket means oxidizing reagent. And I showed you the ones before you could use, but for this class, I'm just going to use it in general. And this is a secondary alcohol. And if we oxidize it, we'll get, you lose this hydrogen and form a carbon oxygen double bond. And this is called a ketone, which you'll learn later on. Like I said, Dr. White loves, oh, I love ketones and aldehydes too. So what's my R groups? Doesn't matter what you call R and R prime. R prime. This is a carbon with the hydroxyl group, which will be this carbon. So I have 1, 2, 3, 4, 5 across. I have a methyl there. This is the carbon with the hydroxyl group. This carbon, which will now, I took off a hydrogen, and I have, and you can have this up or down. And I know there 4 bonds to carbon, if I can draw them nicely. And that's the product you get. That is called a ketone. And I'll teach you about ketones in a couple of chapters. And that's the ketone. Oh, let's do one more. Your turn. This is a hard one, maybe. For those of you with dogs, my sister had a border collie, Pete, who with a tennis ball could go hours on end. He wouldn't let you stop throwing it. All right, I think everybody's done. Let's take a look at this. What do we have? Ooh, hydroxyl group on a carbon. Now notice in the ring, we have carbons here and here. What this really is a secondary alcohol, but in the ring, R and R prime are connected right here. So what happens when you oxidize it? You take, I don't charge extra for dogs, but anyways, you take, hold on, Matt, what's his name? Or her?
His name's Gambit. He's also a border collie. So,
all right. I thought, what was his name again?
Gambit.
Have fun, Pete. At one time, my sister had 4 border collies. She obedience trained them all. Before that, she had sheepdogs. I'll have to show you a picture, the class picture next week. All right. Thank you for sharing. When I saw that, I thought, must be a border collie. I love dogs. But anyways, you lose the hydrogen here, hydrogen there, and you form a carbon oxygen double bond. Well, do you break carbon-carbon single bonds? No. What carbon has the hydroxyl group there? You started with a ring, you better end with a ring, and that carbon is now double bond to oxygen. Unlike aldehydes, you can have a ketone in a ring. We'll talk more about it. And Dr. White and Mother Nature really, and I mean really love cyclic ketones. Oh, let me bring back an old friend. It's old memory time. I did research. This is a very complex ring system. This is called bicyclo 222-octanones. And that's the molecule I did a lot of research for my PhD thesis. Oh, Dr. White's happy now. Old memories come back. What would you oxidize to make that molecule? Boy, am I working you guys hard today. Oh, I think almost everybody's done. I think everybody is just about done. Isn't this organic chemistry really impossible and hard? Not. All right, let's take a look at this. Question is, what do you oxidize? Remember, O in a bracket means oxidizing or oxidation reaction to make this molecule. What's different? What's not a carbon-carbon single bond, carbohydrate? Ooh, an oxygen, and it's double bond to carbon. This is a ketone. We have carbons attached to that carbon. What do you oxidize? A secondary alcohol. In this case, R and R prime are the same, methyl. And you could write it this way. The carbon double bond to oxygen, you start with a carbon with a hydroxyl group, this carbon. And I could have written it this way, or I could have written it this way. Either way would be correct. Now, I'll teach you this again later on, but let's take a look at this molecule right here, that ketone. This is called acetone. That's the common name. And this is one of the two molecules used as nail polish remover. And does everybody see the significance of this reaction? If you're ever trapped on a desert island and you ran out of nail polish remover, but you have rubbing alcohol, which contains isopropyl alcohol or 2-propanol, this alcohol, and if you have oxidizing agent, you can oxidize it and make acetone and remove your nail polish. But you never thought of that. I always think of things like, if I'm stuck on a desert island, I need this, how do I make it? And this is a fun mental exercise Dr. White enjoys. Now, there are three types of alcohols: primary, secondary, and tertiary. And what happens when you oxidize a tertiary alcohol? Nothing, no reaction. Why? Because if you're going to form a carbon-oxygen double bond, this carbon would then have 5 bonds to it, and it won't happen ever. If you find a way of doing that, let me know. We'll be rich beyond my wildest dreams. That goes beyond having my own Lamborghini, my own Ferrari, my own fighter jets to play with, and my own island in the South Pacific. Beyond that, it doesn't happen. Now, listen carefully. When I was an undergrad taking organic chemistry, our instructor would put on a test reactions like that one where the answer is no reactions. And the problem would be, give the reaction product or products are the following: I didn't like that. Why? Well, if you're asking me to give a product, why should the answer be no reaction? Because there's no product. So I teach by my golden rule. I don't do to my students what I don't like done to me. And therefore, I will never, ever put the oxidation of a tertiary alcohol on a test or final, because there will never be a problem I put on my test or final where the answer is no reaction. If you put that down, it's always going to be wrong, because there will never be a question that will be a right answer. So if we go back to the screens, my slide, tertiary alcohols cannot be oxidized. It's no reaction, and this will never be on a test of mine. All right, let's move on. Now, you can have alcohols with more than one hydroxyl group. And we have a name for that, and those are called polyols. I didn't have it on here, but I should. And poly means many. OL is the ending for alcohol. And polyols means many different molecules that have more than one hydroxyl group. And I thought I'd teach you a couple. Let's look at glycols. Glycols is a common name. Let's look at one specific glycol. And this is not the IUPAC name, because nobody ever uses the IUPAC name. The IUPAC name, let me think about it, would be drop the E, ethane, 2 carbons, add OL, but there are 2 of them, and this would be diol. This will never be on a test, but the real name everybody uses is ethylene glycol. And why am I talking about ethylene glycol? Because if you mix this with water, we have a name for that product. It's called antifreeze. And antifreeze is a mixture of ethylene glycol and water. If you've ever seen antifreeze, it's always colored with a dye. Green, I don't know, I've never seen other colors. Anybody else ever see other colors for antifreeze? I think it's mostly green. But anyways, that's to tell you it's not water and you shouldn't drink it. Why? Ethylene glycol is a poison. Now, how does ethylene glycol work in antifreeze? Remember I taught you in melting points the colligative effect? Well, water and ethylene glycol, you get the colligative effect. Now, it turns out there's 2 things that happen with colligative effect. One is you get the freezing point or melting point depression. So if you just had water in your radiator of your car and it goes below 32 degrees Fahrenheit, guess what? It freezes, expands, and you're just going to get a big bill for a new radiator. I don't know how long ago they figured out mixing ethylene glycol and water lowers dramatically the freezing point of water in your radiator. So in the coldest of, that's better, in the coldest of winter in Chicagoland, your radiator won't freeze, which is a good thing. Now, what I didn't teach, but I'll tell you now, is when you have a colligative effect, the freezing point goes lower, but the boiling point goes much higher. And therefore, in the summer in Chicagoland, like tomorrow or tonight, tomorrow, I think when it's going to get in the 90s, or a couple of years ago, or back in 95 when we had a brutal summer, it was 95 or 96, and daytime temperature stayed above 100 for almost a week and a half. That's when hundreds of people died from heat exposure. And that's why we now have cooling centers when we get that kind of brutal temperature. But anyways, that's elevation. Water boils at 100 degrees C, 212 Fahrenheit, But with ethylene glycol, it goes much higher. And that's ethylene glycol, a simple molecule with 2 hydroxyl groups. Let's look at glycerin. Now, glycerin is a common name. Nobody calls it by the IUPAC name, 1,2,3 propane triol. And glycerin, sometimes it's called glycerol, but I call it glycerin. I worked for a company that made glycerin. One thing. Glycerin and this is glycerin. And notice it has not 1, not 2, but 3 hydroxy groups, alcohols. And this is glycerin. Now, I'll teach you later in the semester when your body breaks down fats and oils, it makes glycerin plus something called fatty acids. I'll teach that later on. Now, glycerin, unlike ethylene glycol, is not a poison, and your body makes it, and you can buy it too. Now, remember I talked about alcohols can hydrogen bond. How many of you have ever had those super soft cookies you can buy in the supermarket now? There are a couple different brands like chocolate chip that are soft like that. How do they do that? Well, they put in what's called the humectant. Humectant is a fancy word for something that attracts water and doesn't let something dry out. And this and another polyol are put into things like, what was it, Famous Amos cookies is one of those. And now everybody sells them. Chips Ahoy and everybody else has their soft cookies. And why does a cookie go hard? Because the water evaporates from the cookie, and these keep it in there. Now, unfortunately, another use for glycerin and other humectants is in cigarettes, so this tobacco doesn't get dry. I better tell you, I used to be a chain smoker long time ago. I was so heavily addicted to cigarettes. This is back when you could fly on a plane. I could tell you how many cigarettes I needed in my shirt pocket when I went from O'Hare to various cities in the world or in the country. Don't ask me why. I still remember it. Detroit was 2-cigarette flight from O'Hare. Newark was about 7 or 8. LAX, California was about 10, 12. Manchester and Amsterdam and London were about pack and a half, maybe sometimes more. And luckily in 85, I gave it up, and thank God, because otherwise I'd probably be dead now. If you're smoking, give it up. You'll be happy when you do. I was. Anyways, they use humectants in there. So next time you buy those super moist gooey cookies from the supermarket, they're super moist because the polyol helps keep water in the cookies. Now, another one I showed you, sucrose, has a lot of hydroxyl groups in it. And the last one is polyvinyl alcohol called PVA. Now, most of you have polyvinyl alcohol in your house. You're going to say, no, I don't. Yes, you do. Let's look at the structure of polyvinyl alcohol. Now, I don't know if you remember, but I talked about using parens, and here N, this is like a freight train where this repeats over and over again, and N is on the order of 500,000 to a million. Yep, it's that big. And this is polyvinyl alcohol. And the question is, where's it in my house? Well, if you mix this with some water, you make Elmer's glue, the white glue. And the hydroxyl groups hydrogen bond to the wood, and that's how our paper, and that's how it glues things together. So next time you see some of the white glue, and other companies make it, but the most popular is Elmer. And by the way, I worked for Borden when they just gotten rid of the glue when I started a Borden chemical. And originally there was another polyol called casein that came from rendered horses. You ever heard the old joke in the movie? If you're not a good horse, I'm going to send you to the glue factory. And they used that casein. And later on, it got cheaper to use the artificial polyol, polyvinyl alcohol, this polymer. I'll teach you later on about polymers. So next time you look at Elmer's glue or any of the white glues in the bottle, you're seeing a polyol, a molecule with lots and lots of hydroxyl group. Now, I'm going to turn the switch totally off now, but this is something I think you might find interesting. How many of you ever heard of antioxidants? And you know, they're good for you. If you watch the commercials, what's the one with the dragon for some sort of juice or something like that? It's chock full of antioxidants. Now, what is an antioxidant? Well, it turns out oxygen is a great oxidizing agent. And certain molecules, especially some of those in foods and lubricating oils in your body, react with oxygen to form what's called radicals. And a radical, all right, hold on, my computer is just burping on me. Sorry about this. Every once in a while, it happens. I got so many things running on this computer. All right. Now, an antioxidant, if you have a double bond and you react it in certain ways, and it's got a lot with oxygen, what you'll form is called a radical. And sometimes it's just abbreviated like that. And radicals are very energetic intermediates that react with a lot of things like other molecules with double bonds and things like that. And you don't want radicals in certain things. Now, it turns out antioxidants will neutralize radicals, make them non-reactive. And it's a good thing. Now, about a year or so ago, and I don't know if it's true or not, and I don't think they do either, I heard on the news some doctors were saying radicals formed in our body are the reason we age. Which, is it true or not? I don't know, and I don't think they really know either. But that's one of the reasons maybe antioxidants are good for you. Now, antioxidants, it turns out, antioxidants in nature and the ones we use are phenolic compounds. They have a benzene ring in it with a hydroxyl group and other stuff. And these react to sort of neutralize the radicals so they don't do harm to things like double bonds in food or lubricating oils or other things in your body. And for many years, two of the most popular oxidized antioxidants were BHA and BHT. And that's butylated hydroxyanisole and butylated hydroxytoluene. And now you're going to find out why Dr. White loves T-butyl groups. One of the reasons. All right. Everybody see the structure on your screen? This is BHT, one of the two popular antioxidants, and this is a T-butyl group using the line group method. Second T-butyl group, methyl here, benzene ring with a hydroxyl group, and this helps neutralize it. And there's another antioxidant, BHA. Now, why do I like that? And the answer is, years ago in potato chips, and unfortunately, Dr. White loves potato chips. They love me too, but I shouldn't. But anyways, Lay's sour cream and onion. I just gained 5 pounds thinking about it. But anyways, they would put in potato chips to keep them fresh longer, BHA and BHT. And when I was in college and getting my PhD, my mother would say, "You don't need those potato chips." And I said, "But Mom, they contain antioxidants that are good for me." She never bought that. I don't know why, but she didn't. Now, about 10 years ago, organic chemists found a way of modifying plastic with other organic molecules to stop oxygen from getting into the potato chip bags. And once they did that, and they also fill it now with nitrogen to get any oxygen in the air out of there, guess what? They stay fresher in the bag. So you don't have to worry about them going bad, which is why they put BHA and BHT in there for a longer shelf life. And because of that, now if you look at potato chips, they don't contain antioxidants, but I still love them. I only buy them about 2 or 3 times a year because as soon as I open up a big bag of Lay's potato chips, it just evaporates like that. Speaking about like that, it's time to take a break. I'll see you in 5, come back in 5 minutes. It's time to start again. Everybody ready? Get set. Thank you, Johanna. All right. Now, I was talking about antioxidants, and one thing I forgot to mention, about every couple of years, you hear on the TV and radio some group of scientists saying, like, eat a lot of dark chocolate. It's got a lot of antioxidants. Or before that, it was drink a lot of red wine. And if you eat certain vegetables, you'll get your antioxidants. And I'm not disputing, are they good for you? Yes, I get mine. But I don't know, chocolate, I need that like a hole in the head too. All right, let's get back to work. All right, those are all the reactions on alcohols. So we finished the alcohols chapter. Now there's a lot more in alcohols, and we'll do some reactions later on with alcohols with other functional groups that I'll wait until later. Now it's time for, yes, a new functional group. And I better warn you, this new functional group stinks. I mean, it stinks bad. But at the same time, it helps save lives. But I mean, it's stinky. Oh, is it stinky? What's that new functional group? It's the thiol. And a thiol is the sulfur analog of alcohols. Analog means similar. What is a thiol? Now, THI, thi, is the way in our chemistry we say sulfur. And thiol, OL, alcohol, that means a sulfur alcohol like this, where this is an alcohol. A thiol, you replace the oxygen with a sulfur. And this is called the thiol. Now, until about the late 1980s, early 90s, and I might be off by a couple of years, IUPAC used to call this mercaptans. And I'll still call them mercaptans at times. And mercaptan was another way of saying sulfur. But it became thiol, and now it's called a thiol. And these things stink. And I mean stink. And like I said, they stink. I'm not going to teach you the IUPAC nomenclature for this because we're not going to do much with it. And really, people use common names, but you name them like alcohols. Instead of using an OL ending, use the THIOL ending. And they stink. And like I said, the old name was mercaptan, and I won't do that. Now, I'm going to skip the next slide. And what's something that stinks? Have you ever been around where a skunk let loose? Like it's on another animal? It's skunk odor. And someone somewhere, and it wouldn't be me, did analysis and found in skunks, their defensive weapon contains this thiol, about 45%. It's got a thiol with also a double bond, and this thiol. Why Mother Nature created that, I have no idea. And the remainder is water. And if you've ever been around a skunk, it stinks big time. Oh, by the way, you can oxidize these to sulfones, and the way to get rid of that smell quick like on is use an oxidizing agent. Ask a vet before you do it on a pet, but a dilute solution of potassium permanganate will do that. There are wives' tales that use vinegar or other stuff. Nah, use potassium permanganate. I would. When I worked with sulfurs in the lab, when you wanted to get that stink off, you use potassium permanganate solution on your hands or on your gloves even. All right, now, where do you find thiols? Well, one, the odor of onions and garlic are due to thiols. Now, yeah, they're stinky, but Dr. White loves onions and garlic, especially onions. It comes from my father and uncles. One of their delicacies they used to have were onion sandwiches. Have you ever had an onion sandwich? Take two pieces of good bread like challah. Does everybody know what challah is? Egg twist bread to die for. Now, today I wouldn't do it that way because it's harder to get, but we'd put on schmaltz, which is chicken fat on bread, sort of like butter, but better, more tasty. Slap a couple of raw onion slices and you're in heaven. Also, you don't want to be around anybody else, or I should say they don't want to do you, be around you because the thiols in your breath, you stink. Now, everybody, that's the one bad thing about Zoom. If you're off by a while, the stop button is right here. But anyways, the next thing I want to talk about, you should know. Everybody get the message? You should know. And this is about a tragedy that happened in 1937 in Texas. There's a small, not a small town, but a good sized town in Texas. At this high school, it was brand new and it was really well made. And it was right near the oil fields. And when you make oil, you also generate methane. And methane is the main component, like 99.9%, in natural gas. How many of you have ever smelled natural gas? Anybody ever smell it? Give me a thumbs up if you have. No, you have not smelled, or I should say, how many of you have smelled methane? And the answer is none of you. Methane is odorless. But wait, my natural gas, when there's a leak, I can smell it. And that's because of the following you should know about. And that is, in that high school, there are variations on the story, but the main one was somehow a gas line, because the oil well fields people said, we'll give you free gas, natural gas. And the high school said, sure, we'll take it. And one of the gas pipes leaked. And eventually it filled the whole high school with methane. Methane is very explosive. If you've never worked with explosive gases, and I work with hydrogen in a chemical plant, they go off real easy. See right over here? I don't know if you can see it. Let's see. Right there, my light switch, your light switch in your house, you go click on or off inside, there's going to be a spark every time you turn on or off. In chemical plants where you're using hydrogen, they have special explosion-proof switches. So the spark is inside of something, it won't blow up. Well, anyways, unfortunately, that high school blew up. It killed about 300 students or more and teachers. It was a great tragedy. And because of that tragedy, I don't know how many others were badly burned and injured, lots. The Texas state government created a commission to find out how to make natural gas safe. And they came up with a solution to this day we all use. At least in the United States, I don't know about worldwide, but in the United States we do. And they added a thiol. And the thiol they added was this one. I was just about to call it T-butyl mercaptan. It's really now the common name, T-butyl thiol. That's the common name. And T-butyl thiol stinks. How stinky is it? You know how much they put in natural gas so you can smell it? They only put about 4 parts per, are you ready for this? Billion in natural gas. That's 4 ppb. That means for every billion pounds of methane, they put 4 pounds of this in there, and it still makes it quite stinky. And that makes, because of that very sad tragedy, that now makes all of us safe from gas leaks, because you can smell it. Now for I do, Dr. White's story. Back when I was in grad school at Michigan State, first of all, the chemistry department building when I started was only about 2 or 3 years old, and it's huge. It's about 2 blocks long. This is the chemistry building. It's 5 stories high. It has a penthouse, it has a basement, a sub-basement, and a sub-sub-basement. The basement, sub-basement, and sub-sub-basement are also 2 blocks long. It's huge. We had about 500 people working in that building, and this is the chemistry department. It was just huge. And we'd have fire drills every once in a while. And a chemistry building, when there's a fire drill, you take it seriously. Well, one time, I was about my 3rd or 4th year in grad school. I was at my desk in my lab where I was doing research, and I was sitting there. I wasn't working in chemical reactions. The fire alarm went out. And it was a rainy day in November. I grabbed my winter coat and went out, and everybody else who was in the building grabbed coats. You know better in Michigan in the winter. And we're standing around, the fire department shows up, and they go in, and we were wondering, they would do that when there was a drill also, just to get us to feel this is how it would be real life. And we're out there 5 minutes, 10 minutes. And as in fire drills like that, all the organic grad students would huddle around and talk. The inorganic would be in their group, or other branches, analytical and physical, would be in their groups. 5 minutes, 10 minutes, 15 minutes. And one of the firemen walked by, and I don't know if it was me or another grad student asked, "What's happening? How come we're not going back in?" And the fireman was nice enough to tell us, "We think you have a gas leak." And one of the grad students, and it could have been me or someone else, said, "I wonder what idiot put T-butyl thiol down," and we said mercaptan back then, "down the drain." It turned out some second-year grad student who didn't know any better had some, was finished using it, put it down the drain, the sink, went down to a sub-basement where one of the water traps in the sinks down there hadn't been used so long, it was dried out, and the vapor from that came out of the sink. A janitor down there smelled it, and T-butyl thiol, so they almost let it slip out, said, "Ooh, gas leak," and he did the right thing, called the fire department. They came out, we evaporated. And eventually, about 10, 20 minutes later, they couldn't find anything other than that leak. They tracked down to that. They realized what had probably happened. Now, one of the things the chemistry department had was called the Barney Beaker Award. You never wanted to be the one winning the Barney Beaker Award, and I never did. And the Barney Beaker Award was given to the grad student who did the dumbest thing that semester. And that guy won the Barney Beaker Award. But remember, you're safe now because of that tragedy. If you go to YouTube, I happened to look at it the other day. There are a couple of YouTubes on it. It was quite horrific how badly that school just blew up from the gas leak. Because you couldn't smell methane. No, you can't. Oh, I should say in propane, which you use for your barbecue, because of the solubility difference between methane, and which is a gas under pressure mostly, and propane, which is a liquid, they use another thiol. So when you're doing your barbecue, if that tank leaks, you can smell it also. And we're done for this chapter of alcohols and thiols. Remember, thiol creates the odor in natural gas. That's really the only thing you should remember about thiols. So it's new chapter. Their new functional group time. All right, everybody see chapter 8 on your screens? Thumbs up, people. Thank you. All right, the new functional groups we're going to talk about are ethers and epoxides. And they're quite useful groups, and we'll learn a lot of nice things about that. Let's look at an ether. What is an ether? An ether is where you have an oxygen and two R groups, R and R prime. Now they can be the same or different, and they're both bonded to the oxygen. It's like you replace the hydrogen and the alcohol with an R group. And this is called an ether. Now, nobody uses the IUPAC nomenclature unless you're writing a contract or a patent for ethers. Even the patents use with a common nomenclature. So that's the only thing I'm going to teach you, but I will show you the other one because I do know it, but I'm not going to put it on the test. Remember, this is for test number 2. Now, for ethers, the common name is you name each R group of the ether as an alkyl group and add the word ether at the end of the name. So for common, you name each R group on the oxygen of an ether as an alkyl group and then add the word ether. Examples, see board. Oh, I've got to get to work. All right. Now, an ether would look like this. And how do you know it's an ether? An oxygen with 2 R groups. And how would you name this? This is methyl, this is ethyl. Since it's a common name, not IUPAC, doesn't matter which you put first. You could put methyl, ethyl, ether, or you could put ethyl, methyl, ether. And that's how you name ethers. So I'm going to let you have one to have fun with. What would be the common name for that ether? And don't forget, the lab we talked about yesterday is due Monday. All right, everybody done? I think so. So let's do it. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Oxygen. Notice it has carbons here and carbons here. It's an ether. How do you name it? Common. Name each R group. Let's call that R and R prime, or you can reverse it, doesn't matter which is which. And I call this either isopropyl methyl or methyl isopropyl. Let's do isopropyl methyl. Because this is an isopropyl group. This is a methyl group. if I can spell it right. My brain just put methyl and ethyl together and came out. I think I need a break. And there you go. I got to redeem myself. So let's do another one. And why don't you do this one? What would be the common name for this molecule? All right, I think everybody's done. What's different? Oxygen with carbons here and here. That's an ether. And here we have, oh, an ethyl group, another ethyl group. How do we say 2-diethyl ether? Now, it turns out diethyl ether is probably the most widely used ether in chemistry. It's so widely used in other parts too. It's just sometimes called ether, just like you call tissues Kleenex, or used to. I don't know if they still do. Or we used to call photocopier just a Xerox machine. Go make a Xerox of this. And this is called ether, or diethyl ether. Now, diethyl ether is a liquid at room temperature. Ethers are flammable. Ethers make gasoline look non-flammable. That's how badly flammable. One of the other bad things about diethyl ether is it's more dense or heavier than air. So it doesn't dissipate like gasoline fumes will. You get a little, it will evaporate and dissipate. Ether stays right around here. If this is a bench top. Now, when I was an undergrad at IIT, we had in the research or the teaching labs, they had a trough down the center of the bench, people on each side working, and you could have condensers, which I'll teach you about, water going in there using different things. And back then, we used, this is dangerous, Bunsen burners to heat things in organic lab. We don't do that anymore. And you'd light it with a match. And a number of students would throw the match, which you weren't supposed to, into the trough because there's usually water in there. Well, people would be using ether, and somebody light a match and throw it in there, you'd have an ether fire and just go swoosh like that. Now, the lab I had when I was an undergrad for introductory organic, not me, but we had a bunch of, how should I put this politely, people who decided not to use their brain when they walked in that lab. And we were known as the fire lab. Why? Because out of 16 weeks, we had 15 fires. Nobody was ever badly hurt. And we had a teaching assistant who taught the lab. And he was this little Chinese guy, 5 foot and skinny. Back then in the lab, they had the old heavy 2.5 feet, 3 feet high fire extinguishers. And he could drag those pretty quick. He couldn't even lift it up, but he could drag it and get to the fire real quick. And that's diethyl ether. Now, another important thing about ethers, and the first one was diethyl ether, is their inhalation anesthetics. Back about 1836, they found out when you inhale diethyl ether, it puts you out. And what could that be used for? Well, they're going to operate on you. And where was that heavily used? In the American Civil War. Unfortunately, a lot of people had to be, soldiers had to be operated on. Bad thing about ether is it's flammable and you'd lose surgeons. Back then, you needed a light and you had a oil lamp, it could blow up the ether. And even into the early 1900s, if a surgeon were to cauterize a blood vessel or something with electrical instrument that heats up, and they'd put the patient out with ether, diethyl ether, uh, guess what? You would have a fire. The patient would be dead, and the surgeon, a lot of times, hands were burned. You no longer have a surgeon. Well, how did they find that out or fix that problem? And that is when you replace hydrogens with halogens in an organic molecule, you make it less flammable. And one of the replacements for diethyl ether, does everybody see on their screen isofluorine? Okay. And notice you have an oxygen here, carbon with two fluorines, and it has a hydrogen. They don't show it. Here's two carbons. It's like the analog of methyl ethyl ether, and a chlorine here with two hydrogens and three fluorines. And this is way less flammable, and it'll put people out. Now, long time ago, long time ago, when I moved into this house, I was doing stupid things like when I moved in, I'd pick up 2 boxes of books, a couple 100 pounds to carry them upstairs and all that. And guess what? I had problems with my hernia. I had to have a hernia operation, actually a double hernia operation. And the surgeon I had, which I had heard about from friends, and he was a very good heart surgeon, and he also did that kind of surgery, it was quite good. I was recommended, he said, yeah, you need an operation big time. I've got to go in there and reinforce it. So, because he didn't like working, operating in the morning, my operation started at 1 p.m. So if you've ever been in a hospital, I don't know if it's the same at all, you get there early, they put you in a gown, put you on a gurney, and a half hour or so before they wheel you to the operating room. And you don't go right in there, you wait until the surgeon shows up. This hospital have that. Well, it's I can see a clock on the wall, 5 to 1, 1 o'clock, 5 after. I'm wondering what's going on here. And all the nurses and surgeons there had their gowns on, the caps and everything for the surgery. And one of the nice doctors who turned out to be my anesthesiologist for my operation came over and said, I see you look concerned. Your surgeon is late. I said, oh, really? What? He said, oh, he's always late. He's never on time. He's good, real good, but he's never on time. So to waste time, he asked me, what do you do? I said, I'm an organic chemist. He said, oh, and he brought over a bottle of the isofluorine and said, here's the stuff. I looked at the label and saw the name for it. And I said, here's the structure for it. And he said, oh, I got to get to work. And I said, what's up? Can't you tell your surgeon's here? No, everybody was wearing masks and I didn't know. And it was pretty severe surgery. I was in the operating room for almost 5 hours. And afterward, I got out. By the way, in case you're wondering, I survived. But that ether helped put me under. Now, let's do one. Why don't you draw the structure for ethyl T-butyl ether? By the way, doesn't it feel good to be doing organic chemistry? It's not that difficult. I hope it's not. All right, I think everybody's done. So let's do it. Start here, move that way. Ether, I know this is an ether. And what do we have is R and R prime, a T-butyl group and an ethyl group. It doesn't matter which side you put which on. I'll do this first, then oxygen and ethyl, 4 bonds to carbon. And that's how you do it. Now, let me show you why most people don't use the IUPAC unless you have to. Switches off for this slide. Click, it won't be on test or final ever. Now, IUPAC has nomenclature for everything in organic and chemistry, period. And how do you do that? When you have an ether, and don't write this down, I just want to show you, name the smaller group of the ether as a functional group or a group we call alkoxide. Name the larger group as an alkane. Name and number the alkoxy group as a substituent on the larger group, alkyl group of the ether. See board for, I'll just do one example to show you why we use common when you can. Again, switches off so you don't have to copy this down. Now, the common name for this ether would be methyl and butyl ether. Now, the IUPAC, the longest chain is 1, 2, 3, 4. That would be butane. This group, RO, is called an alkoxy group. And one carbon is called methoxy, 2-ethoxy, and so on. And it's on carbon 1, so this would be 1-methoxy butane. There wouldn't be a space here. By the way, I just did an editor's way of getting rid of a space. I have been an editor. And this is a lot more difficult than this. And organic chemists are lazy, so that's why we always use the common way for ethers. Now, I won't ask this on a test, but ethers, the smaller ones, have very low boiling points. Diethyl ether, your body temperature, if you put it in your hand, it will start boiling and evaporate. And it's flammable. I mean, really dangerously flammable. I remember one time when I was living in this apartment complex, I saw someone, and it was a trick to get a car started in the winter. You sometimes put diethyl ether in the carburetor. So, because it burns much better than gasoline, it helps start the car. I saw the person I said, don't put that much in there. You're going to have a fire. He said, I know what I'm doing. I said, be careful. And he said, I know. And I got the heck out of there. And sure enough, you saw flames coming out of the engine compartment when it started up the car. Luckily, they went out and didn't catch the whole car on fire, but ethers are flammable. Now, how do you make an ether? The main way is the Williamson ether synthesis, and it's named after the chemist Williamson. And you take, this is called an alkoxide, it's made from an alcohol, reacted with an alkyl halide, and you make an ether plus salt. The carbon with the halogen is the carbon that will be bonded here in R prime in your ether. The carbon and the halogen, alkyl halide with the halogen on it, will be the carbon the oxygen's bonded to in your ether. So let's take a look at this. And if we look at this reaction, the question is, what's the product or products you make? Oh, now things are getting really exciting because once again, we have more than one organic molecule reacting. And again, look at what's different. What's not a carbon-carbon single bond or carbon or hydrogen. And right here we have an alkoxide, oxygen with a minus charge on the carbon with sodium cation. All molecules in nature have a net zero charge, which is why you need the cation there. And then what's different here? Carbon, 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 halogen, alkyl halide. I'll call that R prime. X can be chlorine, bromine, or iodine. And this attacks the carbon with the halogen, kicks it out. Did you know organic chemists are violent? We are. Instead of saying forms the bond, we say it attacks it. And it does. And you form ether. And later on, it's good to know you don't have to put it down. It forms a salt, NaX, which is a salt. Time out for a quick Dr. White thing. Everybody know what this is? Sodium chloride, table salt. If you ever go out with chemists or especially organic chemists to a restaurant, I've been guilty of this many, many times. One of us will ask, will you please pass the NaCl? Never mind. All right. I guess it's humorless Thursday. So what's our R methyl? What's our R prime and propyl? Remember, the carbon with the halogen will be bonded to the oxygen. So I have my R group, oxygen. What's R prime? You don't break carbon-carbon single bonds. 3 carbons, ends to the N carbon, and that's the molecule you get. Give you time to write that down. I keep on forgetting. I should give time. Everybody got that written down now? All right. I'm going to let you have some fun. And why don't you do that? What would be the organic product or products? You don't have to put down the salt, but what would be the product you make when you do that reaction? And when you're done, give me a thumbs up or any other emoji you want to do. How many of you have ever seen the Our Gang movies or things where they say, give me the high sign, it's this? I'm showing my childhood. All right, let's take a look at this. I think everybody's done. What do we have that's different here? Oxygen and a minus charge, sodium cation, carbons, and we have an alkoxide. What's different here? Carbon, halogen, alkyl halide. Number X can be chlorine, bromine, or iodine. That's better. And what do you get? You get an ether plus salt and AX. But I'm only asking for the organic product. So this is my R. This is my R prime. Oh, they're the same. And what you get, R oxygen, R prime, the oxygen goes to the carbon with the halogen, is bonded, and we've just made diethyl ether. Oh, let's do another one. Everybody have that down? And have some fun. And I see some people giving me the thumbs up. Notice they don't have thumbs down as emoji. And I wish they did have one like that. But anyways, I better get to work. And I look for what's different. Ooh, oxygen with a minus side, sodium cation, that's the positive, and carbons. I have an alkoxide. Or this is my R group. What's different here? Carbon, carbon, ooh, carbon with a halogen, that's an alkyl halide. And this is the Williamson ether synthesis that attacks that and bonds to the carbon with the halogen. Remember, X can be chlorine, bromine, or iodine. And you also get a salt, but you don't have to put that down. And what's our the cyclopentane ring? What's our prime? This isopropyl. Do you break carbon-carbon single bonds? No. So I have my R group, oxygen. Which carbon has the halogen? The center one. So therefore, center of 3. And that's how you do it. And that's how you make ethers. Like I said, ethers play an important role. One of the most important roles are ethers are very inert to other chemicals. You really have to do something unusual, and I won't talk about it. Treat it with very strong acid to break up an ether. Therefore, they make excellent solvents for organic reactions. Now, I've used diethyl ether, but for my research, when I was doing my PhD work, this is an ether. It's a cyclic ether. Notice oxygen, carbons here, so it's R prime. They're connected together in a ring, and this is called tetrahydrofuran, abbreviated THF. I don't know how many hundreds of gallons I used in my research for that. That was the solvent we used to run reactions in THF. Oh, it's an old friend of mine. Say hello. And that's my old friend. Now, if I look at the clock, there's something that I have to talk about. And I should mention this. Next Thursday is test number 1. Test number 1 is the one that most people get the highest average. So you should be studying the hardest right now. You should do that for every test. Best way to study for my tests are 1, do the practice problems. 2, do the practice problems. And then look at your notes. If you want, look at the video. However, if you can do the practice problems correctly, you'll do fine on my test, which is why I created them, because practice makes perfect. If I look at the clock, I've been driving you hard this last 2 weeks. Don't tell anybody. I'm going to let you out about 2 minutes early. Shh. And with that, I'm going to say goodbye, but I will remind you the lab is due that you did yesterday on Monday. If you have we won't meet until next Monday. So if you have Dr. White withdrawal symptoms, watch me on my YouTube channel. And with that, thank you always for being in my class. And I'll say, Gang gesund, goodbye. Remember, Gang gesund is Yiddish for go in health, be healthy. Gang gesund, goodbye.